thanks for the organizers for this chance to present my talk today. Today I'll speak about adaptive iterative techniques for solving quasilinear non-monotone elliptic PDE. This numerical homogenization will be presented in the framework of LOD techniques, the localized orthogonal decomposition. And this is part of my PhD with my supervisor Barbara Vervoet, and this is funded by DFG. First, I would like to outline my talk. First, I will present the prototypical PDE and speak about the challenges that we might face when solving this PDE via standard numerical techniques. Second, I will also present the LOD techniques and speak about the challenges and issues that we have when we apply these techniques into nonlinear PDEs. And then I will speak about two linearization approaches in order to overcome these challenges. In addition, for each approach, I will present the theoretical findings and convergence analysis, as well as a numerical experiment for each approach. First, this is our prototypical nonlinear PDE, which is defined as the minus divergence of alpha xu, gradient of u equals f in omega with homogeneous Dirichlet boundary condition. And we implicitly assume that we have a rock coefficient where we have spatial multiscale nature with respect to the first argument of alpha and nonlinearity with respect to the second argument. Linear PDEs for new manufactured materials are no longer accurate to predict the physical behavior, for example, negative refractive index, and especially for the high forces and high temperature. However, the nonlinear models accurately does the job. But when trying to solve such a nonlinear PDEs, when we have a multiscale nature, the standard numerical techniques fails. Especially when we have coarse meshes, and the upper bound for this kind of standard numerical techniques depends mainly on the multiscale parameter of multiscale spatial parameter. The other thing, the linear techniques that used to prove the upper bound of the error cannot be applied anymore for nonlinear. For example, the open niche trick. In addition, we assume some high regularity in order to be able, some high regularity assumptions on the solution in order to be able to prove the error bound for the solution and the numerical solution. The model in the weak form is given as follows. Assume we have f in L2. We don't assume for the first step that we have more than L2, and we seek to find the solution in H10 such that it satisfies the following weak formulation. As we can see also, this weak formulation is still nonlinear. Some extra assumptions that we need in order to guarantee the existence of the solution. First, we assume that alpha belongs to L infinity from omega into R when the second argument is fixed. The second assumption is the Lipschitz continuity with respect to the second argument. So that is bounded from above by capital LC, and in addition we assume the ellipticity and the boundedness. Regarding these assumptions, plus the function, the right-hand side in L2, we cannot assume that we have a solution more than H10. And this is the main settings of our problem. And in order to solve this kind of nonlinearity, together with multiscale nature, we aim to decompose our space of function H01 into two orthogonal subspaces. Assume we have VH, the first order Lagrange finite element space built on coarse mesh. The LOD technique depends mainly on the use of suitable projective interpolation operator that maps H10 functions into the finite element function. And because of this projective property, we can decompose H10 into two orthogonal subspaces, the space of images and the space of kernel. And this space of kernel W is called the fine space function. And the main goal is to transfer, because here VH doesn't hold any information or any multiscale information from the problem. So we need to decompose the space into two spaces, the multiscale space and the orthogonal space that's orthogonal on W. And assume for the sake of argument that we can build our space for the nonlinear PDE where we have a nonlinear form here, such that the multiscale space is defined as follow. V in H10 such that V is orthogonal to the space and satisfy the following orthogonality. And if we can do so, this is defined by, this can be defined, or we can transfer the orthogonality from VH into VH multiscale by defining a correction operator that corrects the basis of the finite element space. And this kind of correction is defined from VH into a finite space W, and it's defined to be a orthogonal projection. However, so far we're still not sure if this multiscale space is linear or well-defined, because the correction of LOD is defined in LOD literature based on linear operator. And as I said, assume for the sake of argument that this is well-defined so far. And then after we define the space, we need to localize it. I will not speak more details about localization because it's already presented during the winter semester, and I assume most of the audience are familiar with this kind of computation. And after we define the correction computation, we localize it and truncate the domain of computation into smaller domain. Okay? And suppose that we build this kind of multiscale space after the localization, so we need to solve the nonlinear global problem. The nonlinear global discrete problem is defined as follows. Assume we need to find the multiscale space, multiscale function that lives in the multiscale space such that it satisfies the following form. And this space, VHK, is defined as the span of lambda x, this kind of the basis for the finite element space minus the correction of these lambda bases. But watch out, we have two issues right now. The first issue is the definition of the multiscale space. We are not sure if it's defined or not. However, we have another nonlinearity. So we have two nonlinearities. The first linearity when computing the correction operator, and the second linearity when computing the global discrete problem. And this kind of two linearities makes the problem a bit complicated, where we need extra computation or too much computation to solve this issue. And how can we solve these nonlinearities or solve these issues and the combination between these two nonlinearities? We have two approaches. In order to handle the nonlinearity, the first approach is we construct a multiscale space only once by linearizing the correction operator problem, and then iterate over this multiscale space to solve the global nonlinear problem. The second approach is to construct a multiscale space and then solve a linear problem, then update the multiscale space, solve another linear problem iteratively. For the first one, still we have an issue that it depends on the use of suitable linearization and suitable linearization point to construct the multiscale space, because the correction operator is nonlinear, so we need to linearize the form in order to be able to compute it. For the other approach, where we iterate and build multiscale space iteratively, this is nightmare. I mean, in order to do the computation for the correction in several iterations, this computation is expensive. However, we can find the solution also for this kind of complicated computation and try to adaptively iterate to construct a multiscale space. For the first approach, as we said before, we had the nonlinear operator. However, if we linearize the curly A that we defined before, we can have a bilinear form where Q is a correction that maps the function from VH into W and satisfy the following orthogonality with respect to AL. This A curly L is linear with respect to the second argument and is defined as follows. A curly L is defined to be this kind of linear approximation of this nonlinearity. Okay, we replace the nonlinearity of alpha x v1 multiplied by the gradient by this linear approximation. Okay, now we have a linear approximation or bilinear form, and we can solve the correction operator as presented in the LOD literature, and we can easily define a linear multiscale space by modifying the basis of VH, and at the same time it is orthogonal to the space of fine function.
Sorry, don't you mean alpha x comma p star?
No, because this is the approximation, the linear approximation of this nonlinearity. This is nonlinear.
Okay.
Yeah? And then we can build our linear multiscale space that we are sure that it is defined because of linearity that we have in this definition. The question is how one can linearize and approximate the nonlinearity in this correction operator. One can do so by either Kačanov type linearization or a free shade derivative. For the Kačanov type linearization, we freeze the nonlinearity and replace the second argument of alpha by a function that is chosen from H10. So here we have a linear form. The other linearization is the directional derivative in the direction of v minus p star. Simply, we have it as follow alpha x b star multiplied by the gradient of v plus this extra term. Okay, this extra term appears because of the derivative with respect to the second argument. And as we can see that this AL, the linear form here, or the linear approximation here, and the linear approximation here is linear with respect to the gradient, and here linear with respect to the gradient plus some extra term. And if we have this kind of linearization, one can easily solve this. One can easily solve the correction problem here, and then localize the problem in order to build the multiscale space. And for this approach, we can see that we have upper bound for the error between the solution and the multiscale solution that depends on the discretization parameter h plus localization parameter beta plus linearization term. The constant here does not depend on the multiscale parameter of the spatial term of alpha. And we do not assume more regularity for the solution more than H10. And this linearization term seems to depend on the L infinity norm of the error between U and B star, and the error between the multiscale space and B star, the multiscale function, and B star. Okay, this imposes the question, what is the best choice for B star in order to be able to minimize this error? Okay, we have three choices. The first choice, or the best choice I can suggest, is to choose the coarse finite element solution. We solve the problem on the finite element space and using a coarse mesh, because this kind of function entails some information about the solution, but it's not accurately capture the solution. The second one, we can choose arbitrary guess for P star and choose P star as a linearization point. The third one is choosing a cascade of LOD, which means that we choose a linearization point and solve the problem, and choose the solution of this problem one more time in order to build the multiscale space and get another solution. The second issue here for the previous linearization forms, this kind of term imposes extra assumption for the free shade derivative linearization that we should have small h in order to guarantee the coercitivity of the curly A sub L, the linearization of the linearization form, such that it is coercive on the fine space W when solving the correction problem. And now we show some. I show some numerical study when applying this approach assume we have this nonlinearity where Cx is the conductivity field multiplied by Ku. This Ku is represented by the following exponential model, and the right-hand side is given such that F is defined defined by parts. And the conductivity term Cx is defined as depicted in this picture. And in order to study the convergence performance, we use this relative error definition. For the left-hand side plot, I tried to choose several linearization points that some of them are close to the solution and some of them are far from being close to the solution. And for the first 4 points, I choose P star to be U0 or P star to be the finite element solution or P star to be the Lut function or the cascade of Lut function. I noticed that we have first order convergence. However, when I chose B star to be G, this G is defined on purpose to be very big function of maximum value that's bigger than the analytical solution, because the solution for this problem is somehow has maximum value close to 1, but this G here is a function of big values. And when I choose this linearization point, I lose the convergence. So this means that the linearization point plays an important role when I construct the multiscale space. However, for the Khrais method or for Khrais linearization, I tried the same technique. I tried the same linearization point. I chose the finite element functions, and for the finite element functions, I can see that I have convergence, and then we have increasing. This kind of increasing or tableau results because of the linearization and because of the localization error. But when I choose this function G that is far from the solution, I lose the convergence. However, when I choose the solution, I obtain here one more time, which is P star equals U Lut. The convergence is recovered, so I can see it here in the green plot. Okay, this kind of recovery for the first order convergence motivates the second approach. The second approach that I'm going to present right now is the iterative approach. Let's summarize the first approach. The first approach, I construct a multiscale space via linearization techniques. Then I solve the global discrete problem. I construct the multiscale space via linearization that must not be or should not be the same as the linearization techniques that in order to solve the global discrete problem. However, for this iterative techniques, I first choose P star in H10 as initial linearization point and oversampling parameter, this oversampling parameter for the localization. How do I do this kind of iterative techniques? First, I construct a multiscale space via linearized techniques. Then I solve a linear problem. I obtain a solution, UHK. Of course, this kind of problem here is not exact, doesn't solve the problem. So we have to repeat and iterate. I update P star and choose it as the solution that we obtained here, and construct another multiscale space and solve one more time linear problem iteratively in order to obtain a sequence of multiscale solutions. As I said before, this kind of algorithm is nightmare, so one doesn't need to follow this algorithm because this is computationally expensive. Imagine that, okay, you need to construct or you need to solve correction problem in each iteration. And some aspects for this method, as I said, we have a multiscale solution that is constructed by iterative correction operator, and we solve a Galerkin problem for each iteration, or a Galerkin linear problem for each iteration. And in order to solve this issue that's being computationally expensive, we use adaptive techniques. In this adaptive techniques, the question is right now, what if we have a solution that is not changing, for example, in this part of the domain for each iteration? Do I need to recompute the correction that corresponds to this part of the domain? The answer is no, because, okay, we already have it. Why do I need to solve it if it doesn't change or changes in a very small manner. However, the solution changes in a certain part of the domain. It might change here or change here. So I don't need to recompute the correction operator in this part of the domain. However, we only compute it here and here, where the solution changes in a big way. And right now, I present the adaptive iterative approach for such a problem in order to solve it. The first, this adaptive iterative approach depends on a posteriori error indicator. Okay, I will not present it here, but I will see how can we use it. First, I choose a linearization point in H1. We can also see it as an initial point to solve the nonlinear problem. And choose a tolerance. This tolerance, okay. When can I decide, okay, that the correction here needs to be updated or need not to be updated? So I choose a tolerance, okay, that I'm satisfied with. If the error is bigger than this tolerance, okay, I need to re-update it or recompute it. Otherwise, I don't need to compute it. And we choose the oversampling parameter to be k. For the first iteration, I must compute the correction operator. I must compute the correction operator for each t or for each elements of th. Okay, first I construct the multiscale space via linearized LOD using B star, then solve a Galerkin problem for a linear discrete problem and obtain the first iteration of the solution. And for the second iteration and so on, we iterate for each t in th in the grid. We need to compute the corrector error indicator between the correction that is used. This correction is used to compute the solution in the previous iteration, and this correction that is need to computed after computing the solution. Again, this correction is used in computing the solution in the previous iteration, and this correction is need to be computed using the new solution. But it should not be available. I mean, I can do the error indicator computation without having this correction computation in hand. And after iteration, I compute the error indicator and collect these all t belongs to th that is bigger than the tolerance that I specified at the beginning. And I recomputed only the correction for this t that belongs to capital M, small m. And after computing the correction that corresponds to the elements in this set, I update the correction that we have it from the previous iteration. I mean, I just remove the correction corresponding to t here and update them by recompute the corresponding correction for this t. And then after updating this correction, we can build a new updated multiscale space and solve another Galerkin linear problem that seeks the solution, the adaptive solution, let's say it, in this adaptive modified space, such that the solution satisfies this linear problem. And then we update the linearization point and redo the computation. So the error indicator computation is much cheaper than computing all errors corresponding to all element t. So here we choose just a subset of t that belongs to th and compute the subset of correction computation. Okay, this approach still has some limitation that we will discuss later, but let me briefly introduce the error estimate for this approach. The error estimate assumes we have an adaptive solution that we obtained from the previous adaptive iterative technique minus the solution, so it is bounded from above by this v. This new here is called the, I forgot the name. It should be less than 1. It should be less than 1 in order to obtain the convergence, multiplied by bounded by the discretization parameter and the beta. This beta corresponds to the localization. The more k we have, the more small this kind of this constant, plus the tolerance that I indicated in order to compute the error indicator and decide when we update the correction computation. This nu is defined in two ways, for 2D and 3D. The first issue that appears here that for this analysis or for the error analysis, unfortunately, I need to deal with the estimation of XU for the L2. And in order to estimate L2 here, I cannot assume higher regularity for a gradient of U because I need to assume this L infinity here and sorry, not L infinity. I need to assume it in order to be able to bound the error when we have, for example, alpha x U1 minus alpha x U2 gradient of U L2. This is exactly what I need to bound, so I cannot assume that here is bounded by L infinity because this doesn't contribute in bounding the error. So I need to assume this integrability for f for in 2D. I will explain it also why I need to assume L2 plus epsilon and L2, and for the 3D case I assume that f belongs to L3. Okay, here we assume that also this kind of constant should be less than 1 in order to obtain the convergence that we need of order 1. Some aspects for the error indicator or for the method. First, I will clarify that in each iteration we update the multiscale space and solve the fixed point iteration problem plus computing the error indicator, and this can be repeated several times. The second, I need to assume a smallness assumption for the data in order the fixed point iteration to converge. Now that for the third issue, that I need to treat this kind of nonlinearity such that we have a solution U belongs to omega 1p in this Sobolev space. And the question is, when do I guarantee that the solution belongs to this Sobolev space? And the question, there is a question that was answered, especially in the Prana's book, that how does the integrability of right-hand side affects the integrability of the solution for the Laplacian problem? And the question or the analysis for this that okay, if we assume that T equals the Laplace operator, the inverse operator for T maps in a bounded way from, from H minus into H1 omega, and the question is, can this be extended to omega minus 1 Lb into omega 1b? And the answer is yes, if we assume the regularity for 2D, if we assume that f belongs, for 2D we can guarantee that there is this capital B greater than 4, and for 3D we assume that there is capital B greater than 3, such that the solution for this problem belongs to LP and bounded by f LP for B greater than 2 with capital B. And this is for the Laplacian problem. But the idea here can be extended to general problem using a perturbation argument, so I can refer you to Prana's code book so you can find the proof for it. And in order to solve this issue, I assume that for 2D that we have a right-hand side f belongs to L 2 plus epsilon in order to be able to use Sobolev embedding of LP for in 2D inside in H1 space. And for 3D, I need to assume that it belongs to L3 in order to be able also to bound the error by LP and use the Sobolev embedding theorem. As I see that, okay, I need to assume two different integrability for the right-hand side in order to deal with the error analysis. However, we need extra assumption for the case of 3D. Still, that we need that to impose some assumption on the contrast of the coefficient. It's still not directly applicable for 3D. However, for 2D, it's applicable. Okay, if I can show you some numerical experiments when I use this kind of techniques, and I choose the right-hand side to be this function, and for the domain that is for domain 0, 1, 2 in R2, and the result as follows. In the left-hand side one, I compare two techniques. I use the Newton techniques and Kačanov techniques, where I construct the multiscale space via Newton and solve the global discrete problem also via Newton. When I choose the Newton techniques and choose U star, the initial points to be 0 and the initial points to be the finite element function, I obtain errors that is smaller than errors for the case when I use Kačanov techniques to solve this issue. And second, I compare the two techniques. The first technique, when I construct a multiscale space only once. When I construct it and use a function where the solution is not converging. However, for the adaptive LOD, I use the same function and I obtain the convergence directly. Then I will compare the behavior of the two techniques and the number of the updated or the percentage of the updated bases. For the right-hand side, I use U star to be 0 as initial points, and I compare. This is only for Kačanov. I compare it for two different discretization H, or for two different coarse mesh. For the first one, H equals 1 over 16. We can see that at the beginning we compute all the corrections. We don't have updates for the first iteration. For the first iteration. However, for the second iteration, I recompute all the bases. Then, for the third iteration, I compute 80% of the bases. Then it increases and decreases, as we can see. However, when H is smaller, or when we refine the mesh, we can see that the percentage of the updated is becoming less and less, and converges, as we can see. Converges after a few iterations for the Kačanov techniques. And the main message here: the more we refine the mesh, the less we update the list number of the bases that needs to be updated. For the second plot here, I compare two techniques: the Newton techniques and the Kačanov techniques when I used adaptive iterative solver. For Kačanov techniques, as we can see also, we compute all the correction, then update all of them, and then the number of updated starts to decrease. And the algorithm or the iteration solver terminates after 8 iterations, as we can see here. After 8 iterations, and this dotted lines indicates that there is no continuation for the Kačanov techniques. However, for Newton method, we update a lot of bases, more than Kačanov, and iterates after 15 iterations. So the Newton method needs more iteration in order to converge more iteration than Kačanov. However, if we go back, we can see that both of them have almost the same behavior. This means that we pay extra price for this kind of accuracy, or for smaller error, in order to get better results, but the convergence behavior is still the same as Kačanov. And now let me summarize what I already presented. I already presented the multiscale approach for two multiscale approaches to solve nonlinear, non-monotone, elliptic PDE. I showed that the convergence is of first order in both approaches, in the first approach or in the adaptive iterative approach. I also conclude that Kačanov method iterates faster than in Newton method. However, Newton method is somehow accurate, so one needs to compromise between the price that should be paid for the computation and the accuracy. So far, I don't have any analysis for the Newton techniques because it's a bit hard to assume extra assumption, because as I presented first, it has extra terms that makes the problem, instead of having diffusion problem, we will have convection diffusion problem, and we need to assume the assumption for the convection diffusion problem in order to satisfy the ellipticity and in order to converge. But these assumptions I cannot assume for the setting I have so far. Now for the references, if one interested in the first approach, I can refer you to these two papers. The first paper has been published recently, and the second paper and also the second paper of my supervisor. But for the second approach, the adaptive iterative techniques, I can also refer you to these papers where it is applied into perturbation diffusion and similar coefficients, and to this paper where Roland Maher and Barbara Vervoort applied it to multiscale nonlinear scattering problem. By this, I thank you for your attention.